You may be asking yourself, what does a Harry Potter puzzle have to do with AP Physics 1? Nothing. It's just where I happen to be. My daughter's building that, and what I'm trying to do is help you with the understand how you should have responded to the 2019 AP Physics 1 free response question number 2. This is a 12-point question. Suggested time is 25 minutes. I'm going to try to get this video done well before that 25 minutes. I might have to split it in two, though, with my phone's storage capacity. First thing we got to do is read the problem. So the problem explores how the relative mass of two blocks affect the acceleration of the blocks. Block A rests on a horizontal tabletop. There's negligible friction. Okay, yay, we don't have to worry about friction between block A and the tabletop. Block B hangs from a light string, so we don't have to worry about the mass or the weight of the string. And it runs over a pulley that attaches to block A, as shown above. The pulley has negligible mass. That's really great for us because that means we don't have to worry about any of the rotational inertia of the pulley. They're trying to tell us that it doesn't really factor into the motion of this system. Okay, and then the blocks are released from rest. Okay, also there's negligible friction about the axle of the pulley. Okay, so all we have to do is worry about the force of gravity pulling block B down. Looks like block A, there's a normal force and force of gravity that are offsetting. So the only external unbalanced force is the force of gravity on block B. First thing we want to do is to estimate the magnitude of the acceleration of the blocks after release if block A has much greater mass than block B. It's just an estimate. I'm going to say it's close to 0, okay? Because, well, they do want me to explain my reasoning, and my reasoning goes like this. Block A has a great amount of inertia, and that's due to its mass. Okay, and therefore, it's not going to accelerate very much because there is very little unbalanced force acting, which would be the weight of mass B. Okay, so lots of inertia, very little force, going to be close to 0 acceleration. Now, if it's switched, and this has a lot of mass, and this has very little mass in comparison, I'm going to say that the acceleration is going to be close to g. Okay, so block A has very little inertia, so it's not going to resist the acceleration much. The unbalanced force is due to the weight of B, and B would gravity on B would accelerate at a rate of g. Okay, so block A is not going to interfere with that very much. We're going to have close to a free fall acceleration. All right, moving on, they want us to draw free body diagrams of blocks A and B. They're saying that we don't really, the masses are pretty close, or they want us to make sure we draw and label the forces. Make sure you label, guys. Don't just draw arrows, okay? And never, ever, ever draw components unless you're specifically told to do so, which can't think of an instance where you ever were. So don't worry about drawing, or make sure you don't draw components ever. Okay, so here's what my free body diagrams look like. On block A, I've got gravity going down. Do never, never, never label your gravity vector as little g. Little g is an acceleration vector. You need to either call it m times g or f sub g. There's also a normal force that's balancing that out, but they don't give us a grid here, so you don't have to be that careful with your arrows. Since they are balanced, I'm going to draw them relatively close. Label normal force with an n or a f sub n. Tension force, label with a t or an f sub t. Okay. For the block B, I did draw my tension a little shorter than this one. And if they did have a grid, I would make this tension equal to this tension. But again, they don't have a grid, so I don't really have to worry about my relative size as much. On block B, there's only tension up and gravity down. Okay, moving on. The next thing we want us to do is to derive an equation for the acceleration of the blocks. Now, it is no coincidence that they just had us draw free body diagrams, and now they're asking us to derive an equation. There must be something related, so they must want us to use those equations. Now, you could, what they might look for is you to draw a free body diagram of this one, a Newton's second law statement for this one, and one for this one, and then tie them together, knowing that the acceleration of this block and this block are the same in magnitude. However, I think it saves so much time if you look at it from a system standpoint. So the acceleration of the system will equal the net unbalanced force acting on the system divided by the mass of the system. Okay, and so we know that the net force, the only thing that's unbalanced is the mass of block B times G, right? Because this weight and this normal force are balanced. The tension is internal to the system. And so the only thing unbalanced is the weight of block B. But that force of weight on block B is acting to accelerate both masses, both mass A and mass B. That's the mass of the entire system. That is my acceleration. Next thing we're asked to do is to consider the scenario from part A where the mass of block A is much less than the mass of block B. Does our equation for the acceleration of the blocks agree with my reasoning? And I'm going to say that it does. But let's explain why the acceleration approaches that when A is less than B. You got to do this, guys. You have to. The explanations are the main portion of the credit. My goodness, I can't speak this morning. How is that different than any other morning? All right, so look, if we go back to this equation and the mass of block A is much bigger than the mass of block B, so we can look at this from like a limit standpoint. So the limit as the mass of A, I'm going to have it approach infinity. What's going to happen to the denominator of this? You're going to have an acceleration equal to the mass of block G divided by something that's close to infinity plus the mass of block B, right? That is going to be 0. Okay. The bigger mass A is, the bigger the denominator is, and the smaller then the acceleration is. Oh, I'm so sorry. They asked you to explain the other one. So let's look what happens when mass A is much less, as mass A approaches 0, not infinity. Okay, sorry about that. They asked, you gotta, I was just role playing there. I was trying to show you how you can get in trouble if you don't read carefully. Yeah, let's go with that. So let's look at that equation again. We would have MB times G over MA plus MB, right? Well, as this goes to 0, as that becomes insignificant, you get mass B times G divided by mass B, which is just G, okay? So it does check out. All right, so while the blocks are accelerating, the tension in the vertical portion of the strings is T1. Next, let me go ahead and show you what that says. So for part E, while the blocks are accelerating, the tension in the vertical portion of the string is T1. Next, the pulley of negligible mass is replaced with a second pulley whose mass is not negligible. When the blocks are accelerating in this scenario, the tension in the vertical portion of the string is T2. How do the two tensions compare to each other? Okay, let's think about that. If the pulley does have non-negligible mass, in other words, there is some rotational inertia that we have to consider, is block B going to accelerate faster or slower than if this pulley were a light pulley that had insignificant rotational inertia? It's going to accelerate smaller. So if we say that A1 was the original condition, its acceleration would be bigger than A2, and A2 is when pulley has mass, has significant mass. Okay, if that makes sense, right? If I had a really heavy pulley in here, for example, a really massive pulley, that is, it's going to require some kind of some work to move that pulley. This is going to make block B accelerate a lot slower. Okay, now if we look, the free body diagram for block B is still going to be the same. And like the other thing that's the same is the weight of block B, because its mass didn't change. So if it's accelerating slower, that means the tension must be greater. The tension that's opposing the weight must be greater than it was in the previous scenario. So I'm going to say T2 is greater than T1. And now I'm going to briefly explain my reasoning. I'm going to say that the acceleration is less than original because system has more effective mass. Due to the pulley. Okay. If the acceleration is smaller for that block B, it must have a smaller net force. Okay, you really have to walk them through step by step what's going on here. So there must be a smaller net force. The net force is equal to mb times g minus tension. Since the weight is the same, tension must be bigger for the net force to be smaller. Okay, so have we made a case? Have we explained why T2 is greater than T1? Let's see. We did say that the acceleration is less than the original, and that was because there had to be a smaller net force. The net force is given by this, and that's according to our free body diagram. And this is the same, so T must be bigger. All right, I think we've built a case there. I hope you guys found that helpful. Since we do have a tiny bit of we've got 10 minutes to spare here, even with all my blabbing, right? Let's just go back and consider what we've done here. At the beginning, I guess we don't really have to recap this, but when I got to part B and we identified those forces, the very next thing asks you to come up with an equation for the acceleration of the blocks. Please don't think that's a coincidence, guys. Acceleration should always point you to, when you've just talked about forces, that should always point you to Newton's second law. Okay, so I've got this 10 minutes. I should go back and see if there's anything maybe I've left out, if there needs to be more explanation. Now, if I was taking the test, I would do this process pretty quickly so that I can get on to the next question, because the next question might require more than the 25 minutes than I thought I would need for it. All right, so derive an equation for the acceleration of the blocks after release in terms of those and physical constants. If you need to draw anything other than what you've shown in Part B to assist, use the space below. Do not add anything to the figure in Part B. Well, I think this was very succinct, but I think it was pretty explanatory, though, because this came right from the formula sheet. We made substitutions appropriately. And so I think that is sufficient. This may have been where I would have caught the fact that I looked at the wrong limit originally. So when I read through on section D, and I saw that, oh crap, I was looking for the case where block MA has much less mass than block B. And then I might have reread through part E. But after that, hey, we're looking good. Tomorrow I'll walk you through the next question, question 3. I know you have plenty of stuff to do today, because if you want to do well on that exam today on AP, the YouTube link that I sent, they're going over the kinematics, the rotational kinematics, which I know a lot of us struggled with. So please tune in there, and then at 1 o'clock I will be on Zoom for your for any questions you have that were generated through observing the video or of this particular video. All right, gang, stay safe out there.